Hello, my name is Jason Clark, and today I'll be teaching about Newton's gravitational law. So, quick brief history about this man, as most of you may know him. Sir Isaac Newton was a mastermind in physics back in the 16th century. He is the one who showed us today what calculus is. The legend is that one day he was sleeping under an apple tree when an apple fell on his head and got him to start thinking, how is this possible? This is how the gravitational law became as what we know it as today. The first part of understanding this equation is understanding what it means. Right here we are given the acronym, or the, not equation, but theorem, which helps us understand this gravitational equation. What this says is that the gravitational pull of any given object in the universe is directly proportional to the mass of one object times the mass of another object divided by the distance that separates the two objects squared. Some further breakdown between this is that you need the mass of object 1 times the mass of object 2 divided by the distance, not how far they are apart, but how far their cores are apart, or how far their centers are apart. Right here, what we see is some images which will help us understand this. As you can see in this first image, we have a mass of a single object equivalent to the mass of another object, given by a distance equals 1f, or 1/4. If we were to multiply one of the masses by 2, but keep the other mass the exact same and the distance the exact same, we're going to have 2f. This is because, if we go back towards our equation right here, if we multiply this entire factor by 2, since 1 the m's be multiplied by 2, our gravitational pull should be twice as great. This is why we have a 2f. Same goes for if we were to increase the mass to 3 times the mass, but leave the last mass to a single one as it is, and keep the distance same. If we bring it back over here, if we multiply this by 3, the gravitational pull, or attraction, is going to be 3 times as large. Mass is directly proportional to the gravitational pull. However, distance itself is indirectly proportional to gravitational pull, as shown here. We're back to our original equation with 1 over d equals 1/4. Now, if we were to increase the distance between the two into 2d, but leave the masses as the same, we would get 1/4. This is because if we replace our number right here as the bottom 1 to 2, and then square it, we're going to get 4. Leave these 2 as 1 over 4, and there's your 1/4. However, let's say that we were to reduce the distance not by increasing it, but decreasing the distance to one another, so the distance was half. If we were to put 1/2 into the bottom part of the equation and then square it, we would get 0.25. 1 divided by 0.25 gives you your 4. Right here, what you see is the universal gravitational equation itself. It consists of 3 factors: mass, distance, which you already know of, and something known as the universal gravitational constant. This was found by Sir Isaac Newton when he was doing this calculus back in the 1600s. Today we know that the universal constant has a specific integer value. This value is 6.673 times 10 to the negative 11 Newton meters squared over kilograms squared. The reason for this is because if we were to plug this integer into the value, the meter square will cancel out with the distance beneath it. The kilogram divided by kilogram square will be canceled out with the meter square, and with us only newtons of force, and that's where we get the gravitational attraction towards one another. All right, the final logistics to understand is an application. I'll be using 2 body masses for this example. The first being Earth itself. In prior time, I looked up that the mass of Earth is known to be 5.98 times 10 to the 24 kilograms. The second body mass that I'm going to use is a physics student, or any student in particular, and I just gave him a random mass of 70 kilograms. I then want to use the distance of 6.38 times 10 to the 6th, because the student is standing on Earth, and that is the known distance from Earth's center to the surface. So once we plug on all these variables, the universal gravitational constant, the distance, the mass of both of these, we get a value of 686.24 newtons. that is the mass, or actually better yet, that's the weight at which the student weighs, how much gravitational pull the two objects have on one another. Right here we have our final mass. What we can do is use Newton's second law to find the given acceleration of any known object in the universe. So if we use Newton's second law, which is F equals ma, we know the force, we know the mass, we do 686.24 over 70, we can get our mass, or our acceleration, to be 9.8, which is relatively equal to Earth's gravity. This is very useful, but it can be derived into a simpler equation, which I have not created, but it's not being called, so I'm just going to nickname it Clark's gravitational acceleration equation. It can be shown as this. It's the exact same equation as before, but now with only one altercation. We changed the distance into radius, because we use the distance from Earth's center to its surface, which is also known as its radius. However, if we were to remove the mass of object 2, and leave it as it is, will we be given the acceleration? For example, we were to plug in our mass, we were to plug in Earth's mass into the distance we have, as well as universal gravitational constant, we would get the exact same answer as before, giving us our gravity. And this can be used for any known object in the universe: planets, solar systems, suns, people, books, anything. So as I can conclude, the universal gravitational equation is a very useful item which we use all today, and is highly efficient, and it will soon one day, or if not today, will help us explore more of the universe, even in the areas of exploration in space which we have not yet done. Thank you. Goodbye. The first part of understanding the universal gravitational law is understanding its equation, which is as shown. Yeah. Marker just died.